Hello everyone, this is Dr. Dave with Physics 150. I've been getting a lot of requests from students asking us to clarify what they're supposed to do, wanting more examples worked out. And so I wanted to address that quickly in this video and then just give you an example of a problem and the sorts of things that we're looking for. I'm solving this problem without regard to either problem 1, 2, or 3. I'm simply doing what the problem asks me to do. Some of these steps will be helpful for you in different places. One of the big concerns that we have with providing students with solutions and work problems is that they often see it as a checklist. They say, that's the thing that I'm supposed to do, and I'll just do that every time. And then they do what we do, and they don't get full credit, and they want to know why. Physics is very frustrating. And one of the reasons it can be quite frustrating is that you expect to know how to do the problem when you read it. And that's really the wrong viewpoint. You can't know how to do a problem that you've never done before. So when you start reading a problem and you feel really nervous and uneasy about it, congratulations, you're now doing physics. And I mean that sincerely. I have no exaggeration when I say this. When presented with a brand new problem, I read it and my stomach kind of churns from it. I go, oh, what am I supposed to do here? And then I get working. This is the natural part of physics. This is not another type of course that you've done before. I really want to stress that the unease and discomfort when you start reading a problem is really part of the process. The point isn't how do I solve this problem, because every problem is going to have a different solution. So let's start here and let's just go through it sentence by sentence, right? So first sentence, your roommate drops a tennis ball out of a third-story balcony. Great. I don't know anything about this problem, but I'm just going to draw a building, and I'm going to denote that that's my third story. I'm going to put my little window here. I'm going to imagine the ball dropping from there, right? And is that all of the information, right? So again, we're focusing on just this first sentence. The roommate drops a tennis ball from a third-story balcony. Well, there's a little bit more in here. Drops, right? What does that mean? Well, that's one of our kind of code words. That means released from rest. What does rest mean? Well, it means generally that something wasn't moving when you let go of it. So we've dropped something from that third-story window, and we're now going to denote that at this point, the velocity here is equal to 0, right? And we're just going to remind ourselves that this is where the drop occurred. Okay. All right, what's the next sentence tell us? It hits the sidewalk, okay? So that means we need a spot where it hits the sidewalk, right? So that's hit sidewalk. I'm going to use the benefit of my colors here. And bounces as high as the second story. Okay. So that's the third story. Then this is about halfway. So we need about 2/3 of the way. We'll say that is my second story. So it hits and it bounces. Now it's going to get confusing here if I draw all these points along the same line. So I'm going to just separate them over here a little bit. Okay. So it hits the sidewalk. We got hits the sidewalk. Check. We got that. Bounces as high as the second story. Check. We got that. Now what does it mean? Is that everything? Well, bounces as high as the second story. So why doesn't it go higher? Or what do we know about it because it doesn't go higher? We know what? We know that at that point it turns back around. And turning back around is the same thing as like saying dropped. At that point, the velocity is 0 again. Now I want to really stress here, we haven't started using any equations. We haven't started really doing any math. I haven't even read the entire problem yet. And that's really how we want you to approach this. We really want you to just read it, draw it, synthesize it in real time, and see what you get. Now I want to be a little clear here. I'm going to write after the bounce. Okay, and you might find out sometimes, as I might here in a moment, that when you're solving a problem, you do a bunch of work that you don't need to. And oh well, it's really good practice. Okay, draw a complete motion diagram of the tennis ball from the time it is released. Okay, so we need a motion diagram from the time it was released. Okay, until it reaches the maximum height on its bounce. Okay, released to max height after bounce. And when we see these words like big, small, or something, they tell us something. So maximum height, right? So what does maximum height mean? That's often going to mean something like your speed is 0, which is already what we knew after the bounce. Okay. And then be sure to determine and show acceleration at the lowest point. All right, we'll get to that next. Determine acceleration at lowest point. So one of the first things I really advise students to do is, like, once you've got a picture, and I've got one drawn here, okay, you want to begin adding details to that picture, such as a coordinate system. It's one of the most useful things. What is going to be your x direction, your y direction, what's going to be positive, what's going to be negative. Myself, I don't like negative numbers if I don't have to, so I often will choose my lowest point as 0 and up as being positive, but sometimes it's more convenient to pick the top. Sometimes it would help to put your top 0 here. It really just depends. So what I'm going to do, and how do you know? You do a lot of problems, you make a lot of mistakes. That's really it. Okay. So I'm going to add my coordinate system, but first I'm going to put a point 1 here, a point 2 here, and a point 3 here. Okay. And I'm just going to write myself a note to make sure I know what I'm doing here. So 1, drop ball. Okay. 2, bounce. 3, reach max height. Now I'm doing that not because I'm likely to forget that information, but because as I'm solving the problem, I might realize that I'm doing something wrong when I see those words. All right, so I'm going to now do a motion diagram, we need a coordinate system, so we're going to add the coordinate system on there. And I'm going to say that this is my 0 here, and I'm going to say up is positive. So I'll draw that in as the following. And I'm going to say that's plus y, so that's my positive direction. And then here is going to be my y equals 0. All right. Now, we could also add an x coordinate if we wanted, positive x. However, this problem doesn't seem like it needs it, right? The object is moving in a line. That's one dimension. All right. So what I'm going to do now is off my picture, draw my motion diagram. Could you draw your motion diagram on your picture? Sure. But you run the risk of getting really messy. So big thing to remember about motion diagrams, and your textbook author states this, is that you want to draw your dots equally spaced from one another in time, not in distance, in time. So what you want the way that we show if something's speeding up or slowing down is by the distance between the dots. So I'm going to put my first dot right here for my motion diagram. This is going to be my drop. And I'm going to call that my time equals 0 point. Actually, I'm going to just call it my t0 point. And when I let go of it, is it moving fast or slow, right? We know this. We've dropped a ball. It's moving slow. So my next dot is going to be pretty close together, okay? And I'm going to call that point 1 or t1. My next dot, right, is going to be what? Further than that. It's going to be something like here because it's going faster over the same time interval. So I'll call that point 2. And then I know that the object's continuing to speed up as it falls until it reaches the ground. So I have to go even further next time, and I'll just say that's my point 3. Again, we're just eyeballing here because we're trying to be indicative of the motion. And then we'll call that point 4 as it's traveling pretty fast, and I'll call that point 5. And we'll call this the ground. Okay. All right. So what does a motion diagram need, right? I've got a series of dots. It's helpful to then add velocity vectors. And these are average velocity vectors. So we'll say, okay, there is V1 average. And we draw these sort of from point to point. There's my V2 average. Here is my V3 average and V4 average, okay, and then V5. And actually I'm going to put a second subscript to denote it's over the interval. Okay. All right, so that is my drop. And that's it. Okay. Now there's a bounce though. So what's happening at the bounce, right? And you think about that, it's going to be a little bit more complicated because what's happening, let's talk about after the bounce, okay? So we're going to say that the bounce takes some amount of time. I don't necessarily know how long it is, but I'm going to put another dot over here. I'm not going to label it right this minute. And this is going to be the time when the object is going back up into the air. So the first question is, how fast into the air is it going? And you might think it's going the same speed it hits the ground. Well, if it were going the same speed that it hit the ground, wouldn't it reach the same height it was dropped from? And it doesn't, right? So because it doesn't reach the same height, we know it's going slower. So how close should that next point be? It shouldn't be here, right? It should be here because it's going slower. So I'm going to put my next point here. Oops. Next point here. And then I need to put my next point, a next point, a next point. But before we get there, I'm just going to say, okay, let's look at these velocity vectors now. So I have to label this point over here. And I don't really know at what time that point is occurring. So I'm going to just call it 6, but know that that's a little bit problematic because I don't necessarily know when it happened. And I'll call that point 7. And then I know it's slowing down, and so this would be, say, 0.8, and then it's slowing down, we'll say 0.9, and then maybe stops here at 0.10, something like that. So what do I have? I want to make sure I label my vectors, v7,6, v8,7, v9,8. Now, are you supposed to do this on all of your problems? No. I'm simply giving an example of kind of what's going on. So what happened between 0.5 and 0.6? Well, my velocity was down, right? So let's copy that. Now, I realize not everyone has the same kind of tech that I do, but there's my velocity going down, 5.4. That's my average velocity. And then there's my velocity going up. So if we want to calculate acceleration, which is what this problem is asking us about, what is acceleration? Acceleration, at least on average, is the change of velocity over the change of time. Okay, so that means velocity later minus velocity earlier over, time later minus time early. Okay. So for vectors, a minus sign simply means you change the direction. So your textbook might write it, the following. They might write it as v later plus a minus v early. Okay. And if that works for you, great. The best thing to do with vectors is the thing that you don't get it wrong. All right. So then what I'm going to do is say, okay, this vector minus that vector equals what? Well, I know this is a lot of steps here. If you get this, great, just do it. You don't have to do all these steps. I'm just simply trying to help. So now that's velocity 5.4. Okay. Now, again, the negative sign just flips that vector the other way. So, and we're going to then add it, flip the other way. And so you add vectors by placing the tail of one vector at the tip of the other vector. Okay. And so this vector is minus v7,6. So when I add those together, I'm going to have this vector here. Okay. And that's going to be my change in velocity vector. Okay. So, if you're watching this video, you're going to realize that I have made a big mistake. Maybe you've realized what I'm doing all along was wrong. Maybe I should edit it out and do it correctly. I'm not going to, because I want you to see that we make mistakes. So what did I do wrong? What did I say? By writing these words, I caught it. V later minus V early. What's the later velocity? It's this one. That's the earlier velocity. I did it backwards. And that's really important. We all make mistakes, but we have to catch them. So what is it really supposed to be? This is wrong. It should be V7,6 minus V5,4. Okay. So it should be that vector minus that vector, right? And that's the v5, 4. So then it should be this vector plus that vector, which is then going to give us a longer vector. So it's the one that I indicated, except it's the opposite direction. Okay. So what's our takeaway here? The change in velocity is going to be what? It's going to be a vector directed upwards. Okay. And so what is acceleration? As we said, acceleration is change of velocity over change in time. So the acceleration vector will also be upward because our time interval is always going to be positive. So then what do we know? Let's go back to our picture. We know the ball was dropped, it reached the ground, and it bounced back to here. Well, during its time with contact with the ground, it bounced back up. Right? So therefore it had to have accelerated upwards to change its direction. Okay. So we were asked to draw the motion diagram. We've done that. Be sure to determine and show the acceleration at the lowest point. So we have now shown that that acceleration goes upward. So is there more that we can do here? Well, there is, and we'll do a little bit more. And again, you don't necessarily have to do this in all of your problems. You only have to do the parts of it that you need for the correct solution. And I realize that sounds vague and ambiguous and frustrating, and welcome to Physics 150. That's how it is sometimes. So, okay, what's happening as it reaches the bottom? Let's zoom in. So if this is the ground and this is the ball, right? Until the ball touches the ground, it's falling and speeding up as normal. Okay. But at the moment it reaches the ground, right? You may have seen in your life videos or images of a slow motion or stop motion or something. What does the ball do? It ends up smushing a little bit, and I'm drawing this very exaggerated, so it smushes out. And then it kind of reverses the process going upwards, right? Until it's back to the ball shape again, and now it's leaving, right? So it's going down, it's still going down, maybe it's velocity 0 here, and now it's beginning to bounce back up. So the ball is acting like a spring, storing elastic energy that it then returns by pushing back on the ground and launching itself into the air. And is the ball a perfect spring? The answer is no. How do we know that? Well, it just bounces high. So what does the acceleration actually look like? Well, initially, in this case, the acceleration is going to be less than 0 because upward is positive for us. But as soon as this begins happening, right, what's going on? Now the acceleration is directed upwards, right? Because now the ground is pushing on it upwards. The ball is still moving downwards, right? So now here, our acceleration, it might still be speeding up down, but you might think it's still speeding up downwards, but it's not, right? Because now it's slowing. So that means the acceleration is now greater than 0. And here's still greater than 0. And here's still greater than 0, and here's still greater than 0. And once it leaves the ground, what happens? Well, then we go back to the acceleration being negative again. I hope this was less confusing, or how about this? I hope this confused you less than you already were. Please ask questions if you have them. I thought this might be helpful. Have a great day.